have a bubble connected to another bubble, the smaller bubble, because it has a smaller volume, will have a higher pressure than the larger bubble with the larger volume. So since pressure and volume are inversely related, you decrease volume, pressure goes up. You increase volume, pressure goes down. If these bubbles are made out of water, then the higher pressure bubble will empty into the lower pressure bubble. And you can set up an experiment like that in the lab. You can make bubbles, and then you can open one bubble, a smaller bubble, into a larger bubble, and the smaller bubble will just disappear, and the bigger bubble will get bigger. And you can do that with soap bubbles, and that works pretty good. You have to be very skilled with your little needle to poke that hole so that the bubbles don't just break on you. But you can get the smaller bubbles to empty into the bigger bubbles. Alveoli, as we said on last week, Thursday, and early in the chapter, you see the alveoli. They're not all the same size. So there's small alveoli, medium-sized alveoli, and big alveoli. If they were lined with water, the small alveoli would have a higher pressure, and they would push the gas into the medium one. And then the medium one, if it's not as big as the large one, it would empty into the large one. And so you lose two alveoli for gas exchange. You have one alveoli that's very big, but it's still got the same number of blood vessels associated with it. So you've lost 2/3 of your ability to gas exchange. Lung solves the problem with surfactant. The surfactant will get in between the water molecules that want to close the bubble down, close the alveoli down, and equalize the pressure between a small and a large alveolus, small, medium, and large alveoli. They all will have the same pressure. They still have different volumes, but the surface tension of water, which is going to be relating to the collapse of small alveoli into big alveoli, that will be eliminated, and all the alveoli will stay open. The law of Laplace says you look at the surface tension, find out what the surface tension is, multiply it by 2, and then divide it by the radius of the alveolus or water bubble. That will then give you the pressure. So pressure in a bubble is related to 2 times the surface tension divided by the radius of the bubble. So here we've got 2 times the surface tension divided by the radius. Doesn't really matter what T is, because the surface tension is going to be the same for both bubbles. You're going to multiply by 2 and divide by the radius. So P1 here will be, after you do all the crunching of the numbers, 2 times the surface tension. For this scenario, you've got 2 times the surface tension divided by the radius, but the radius is 2. So crunch the numbers. 2 divided by 2 is 1. So the P2, this should be T, but that's wrong. Just see that now. So 2's cancel, that's 1. So pressure here is the surface tension, 1. They have it corrected here, but not over there. So here we've got pressure equals to 1 times the surface tension. Here we've got pressure equal to 2 times the surface tension. So pressure is higher here, lower here. Air will leave this alveolus and enter that alveolus down its pressure gradient. So what do? You have surfactant come into play. So you've got all these little molecules. They're showing you, I guess, phospholipid there. But there's also cholesterol, dipalmitidylphosphatidylcholine, that's the best word there, sialic acid, and glycoproteins. And you've got equal number of surfactant molecules in both alveoli. But the smaller alveolus will have all the surfactant compressed and in between water molecules. So it's acting as though there's more surfactant there because there's less space for those molecules. That is pushing water molecules apart, so keeping fewer water molecules actually in the small alveolus. Here you got the same number of surfactant molecules, but they're over a greater surface area. So you have a little more water in that bigger bubble, which is increasing the surface tension, but it actually will, the number of surfactant in all the alveoli and the number of water molecules available due to the number of surfactant molecules in proximity of each other to interact, you'll get the same surface tension. So here we've got 2 times surface tension, but since these surfactant molecules are pushing water further apart, it's actually decreasing the ability for water to interact to 1/2 of its original capability. So 1/2 the surface tension. Crunch the numbers, now you have 1/1 and the pressure is equal to 1 times surface tension. Over here, we've got 2 times the surface tension divided by the radius, which is 2, and then you crunch the numbers, and P2 is equal to 1 times surface tension. So you've got surface tension, so I've got pressure here equal to pressure here, no gases moving between alveoli. So this is the importance of the role of surfactant, is to get in between water molecules to equilibrate the interaction of water molecules with one another. And you have the same number of surfactant in both alveoli, but here the surface area is bigger, so there's more water attracting water here, and less water attracting water here. It ends up decreasing surface tension here by 1/2 and causing the pressure to go down by 1/2. You end up with P1 equal to 1 times the surface tension, which is equal to P2 1 times the surface tension. Think about it. If you don't understand it, come and see me. Okay, take a break.